Hi guys. Play. Hi guys. Welcome to the question solving session. Alright, so we're left with one question to solve in the inverters, right? But we'll see as we are solving these questions, there'll be a question like that here, so we'll just deal with it. Okay. If not, then we'll go back and solve it because of time. So yeah. So right now, this is what we are dealing with right now. Right? This is what we are crossing our fingers and hoping that the Lord does us good and that we get questions like this to solve. So the first set of questions is this. So we'll go through and look for all questions on this and solve. So a bridge circuit comprising of 4 transistors and associated with anti-parallel diodes is arranged to give unity displacement factor single phase AC-DC converter with bidirectional power flow capability. So the circuit is operated with a DC link voltage of 500 volts and fed from it. So this is what's one. Know that what it's an AC-DC converter. So we're talking about H bridge acting as what? And a rectifier, sorry. So that was the last thing we looked at. So we are having your H bridge here. Oh, sorry. We're having our H bridge here like this, right? And we are seeing how this H bridge will take some AC from here and then how to give us DC. So we know the setup already. So let me just, they say the output is what? Is it 500 volts? Yeah, 500 volts. And then the AC is 200 volts at 50 hertz. So we are seeing 240 volts at 50 hertz, right? So don't forget that we said this are V1. There will be some V2 RMS here. You remember that? Yes, here we have a pulse modulated signal here, but we'll be working with just the RMS value of it. Sure. Then the DC link power is 10 kilowatts. So the power here is 10 kilowatts. The power at the output, let me call it PDC, is 10 kilowatts. PDC is 10 kilowatts. Don't forget that we say PDC is equal to PAC. We mentioned that, assuming it's ideal, PDC is equal to PAC, which means that the power at the input is also what? P in is also 10. Sorry. P in is also what? 10 kilowatts. Okay, now let's say that what? A high frequency PW scheme is used to control the bridge, and consequently the effect of switching harmonics may be neglected. The modulation index is this. So if you're given modulation index is what? 0.716. Sure. The first question says that what? Determine the RMS of the fundamental. We know that modulation index is equal to what? Peak of the fundamental over E. So if I find the peak and divide by √2, I'll get the RMS, right? So now this peak is what? Is the fundamental for this V2. Don't forget, not so let me make it V2 fundamental, V2F. So here MI 0.716 times E 500. Then let me just change it to RMS. So divide by root 2. So that's going to give us, so 0.716 times 500 over square root of 2. That's 253. 253.1. 253.1. So this is the answer here. 253. This is the answer. Now let's move on and look for the other age bridge question. So yes, this is a continuation of the question. That the same question. Find the value of the DC side capacitance required to limit the 100 Hz component of the ripple voltage on the DC side to 20 volts peak to peak. So we said that what? We said that they said find the what? Find the capacitance. So we say that delta E peak is given by what? Delta E peak is given by V, this V here, V2 fundamental times I fundamental. Let me just call it IAC. That's the current flowing through here. IAC, right? The current from this side. RMS over 2E multiplying 1 over omega C. Now the question says find the what? Omega, the C. Find the capacitance. So C is equal to V2 fundamental times IAC RMS all over 2E times omega times delta E peak. In the question, they gave us delta E peak to peak. So divide by 2 to get a peak. We've also found the V2 RMS from here. So 253.1 times, how do I find this IRMS? Now, watch something here. I've been given power. I know input voltage, so I can find what? IAC. So IAC is power over input. So I can write this current as 10 kilo over 240, just for this current here. So this over 2 times E, 500 times omega. Omega is 2 pi F. F is 50 Hertz. So that's 2 pi, that's 100 pi times, here they give us the peak to peak to be 20. So peak will be 10. So times 10. So let's do this. You take your time, I guess it's wrong. Yeah, 100 pi times 10. So you get the answer to be equal to, yeah. So you get the answer to be 3360 microfarad. You get the answer to be 3360. Let me see. 1, 2, 3, 4, 5, 6. I think I missed. That's it actually. Just a bit. Maybe with the decimal point. 1, 2, 3, 4, 5. No. I'm coming. Okay. I'm coming. 10 times, I'm coming. Is what? 10 kilowatts, right? So that's 10 times 10 to the 3 over 240 over 2 times 500. I've seen a mistake. Yeah. Alright. So you get, so this the answer you get is, you get 3.357. You get 3.357 millifarad. Then you move it here. So 1, 2, 3. Then I'll give it 3, 3. Then they rounded it off to 30 microfarad. So that's the answer. So yes. Now let's do for the other questions on the converter. The other questions on the converter. All right, let's keep scrolling. Keep scrolling down. Keep scrolling down. Keep scrolling down. Ah, I'm coming. Papa, there are just two questions on it. There are just two questions on it. You kindly hold, okay? I'm checking if we solved, like, there are just two questions on it. Or time is missing. So that's it. I was seeing some H bridge plenty. All right. And I be we solve that one. Am I muted? Sure, I'm not muted. Rectifier question again. Me too. I'm sure there are other types. All right, sure. No one. Yeah. This is the fundamental. Here, that's what we found it. That's like this here. Fundamental of this B2 here times RMS current, but they give us power. We can find it IAC, and then we put this inside. They give us peak to peak, so we find peak. That'll give us 10 omega. Give us this 100 pi here. We're giving the peak to peak. We're giving peak to peak. Where is it? We're giving peak to peak as 20, so we find peak as 10. Is any more questions from my end here? All right. So we have some people here asking us questions here, so that like hopefully those are the questions that we all have to. Yeah, please use find the current. Please find the current. All right, please let's move on. Power semiconductor devices are mounted on the following heat sink for the following reasons, except so to ensure maximum junction temperature is below a given threshold. This one is true. To reduce the average working temperature on the cycle, yes. To ensure the case temperature is always equal to the ambient temperature. No, this is not true. This one that's not true. Because we're supposed to take the heat from the case temperature. So it's device to case to heat sink, then to ambient. So you're just supposed to take the heat and take it to the ambient. Imagine ensure that they are the same or something. Sure. So there's a single phase rectifier diode question here. A single phase rectifier diode. So you were like, he gave us the formula here. So let's move on. So let's do for all this. So this a single phase diode rectifier is fed from a 240 volt 50 hertz supply with effective inductance of this, which means there will be overlap. Right? There's an input inductance, so there will be overlap. The mean bridge output voltage is 205 volts. Assume the DC current is smooth. You may use the following result where, so we have this. Assume it has a given as delta I to be 5 amps peak to peak, and the overlap angle is 25. The overlap angle is 25. Calculate the DC side smoothing inductance. So we know that L is equal to what? Voltage time area over delta I, right? And then we know that the output voltage must look like this. It must look like this, right? But then due to the overlap will reduce the output voltage, so this part of it will be cut off. So I have the voltage looking like this. We'll have the voltage looking like this, right? And they say what? They say assume the overlap angle. So given as the overlap angle here to be what? To be 25. So we have here to be 25, right? Now they say that we are supposed to find out the VT. We know that what? We know that for a rectifier, right? If you're trying to change AC to DC, so at the DC side, there will be some constant voltage at the DC. That's what when we do this, VDC is equal to 2 root 2 line voltage over pi minus. This is what we find, right? Here they're giving us that the mean bridge output voltage is 205. So we have here to be now. So this is the mean, but you see that what? This part exceeds the mean value. So it is this region that's responsible for the ripple. So in the question, they say find the inductance, right? So the question says that calculate the DC side smoothing inductance. Assume the DC side current has a ripple of this, right? So this ripple is caused by this area here. So if I'm saying L is equal to voltage time area over delta I, then I'm talking about this area. I explained that in one of the videos. So we must find this area. That's what we must do. So the idea is that first calculate the entire area here, right? And then subtract the area of this rectangle here. We just neglect this area here and find this area. So let me call that area A. It's given by the area of the sine. Therefore, sine is always E over omega cos of what? Cos of the small angle, 25, right? Minus cos of some big angle. Let me just say. So let's say that big angle is from here to here. From here to here, that's theta. Minus, so this area minus area of rectangle here, which is given by length times breadth. So the length is what? Is this angle minus this. So the length will be given by theta minus 25 multiplied by breadth. Breadth is this distance. From here to here is this is a height 205, right? 205 over. Now we see that this distance here is in angular displacement. Right? But you know that theta is equal to omega is equal to theta over time. Right? So you want to change it to time domain. That's theta over omega. You get it? By f. But because it's in degrees, your 2 pi will be 360. So omega f. But this is in degrees, so 360. So now the only thing we don't know here is this theta. But we can find at theta, at this point here, this line, the curve intersects with this line. So at this point, let me say at point M, I'll say E sine theta, where E sine theta is the sine curve, is equal to 205 because they intersect at that point. Theta is equal to sine inverse of 205 over E. E is what? Voltage. So root 2 times this. So 240 root 2 will give us our theta. So kindly do that. Sine inverse of 205 over 240 root 2. Yeah. No, but I want to subtract from. So after when you get 37.1, then you subtract from 180. You want the bigger angle rather. That'll give you 142.8. 142. So this is a big angle. It goes above 90 degrees. So that's 142.8. So now it means I'm doing what? I'm doing E. E is what? 240 root 2 over omega. Omega is 2 pi f. F is what? F is 50. So 100 pi. Multiplying cos 25, 142.8 minus 142.8 minus 25 times 205 over 360 times 50. If you must take your time. So you do 240 root 2 over 100 pi times open bracket cos of the answer is also cos answer minus fraction at the top. I'm having what? I'm having 142.8 minus 25 times 205 over 360 times 50. Hey, share times. So you get something. So I think you get 0.4986. Then divide by the delta I. The delta I also delta I was 5. But that 5 peak to peak here 5. So divided by 5. Wow. I didn't get the answer. I'm getting 0.0997. That's giving me what? You were showing me something yesterday, but I wasn't paying attention. But we are still verifying answers, so let's move on, okay? Also, yes, but this answer I'm getting as of now. But we will verify it to see. So let's see if there's any other question on a single phase diode with these same parameters. Let's see. Please, it's what? A single phase is here. So they said determine the DC current. A single phase diode rectifier is fed from a 240 volt 50 hertz supply. Let's try to draw it, which has an effective inductance of this, right? The mean bridge output voltage is this. Assume the DC current is smooth. Okay. Please check. Let's check this one. Because I don't know why we're not getting. Can you check the one we solved right now? Okay. All right. So for that one, I'm not sure we are getting. Okay, we are back. It's given by 2 root 2 times supply voltage. That's 240 over pi omega over pi. The question says find the DC current. You're supposed to find the ID. So in the question, we've been given everything. We've been given times pi over 2 ls omega. Yes. So my ID is equal to this. So ID is equal to this. So my ID is given by putting everything 2 root 2 s. Ls is what we're giving inductance, right? 1 milli. So 1 times 10 to the negative 3 times omega. Omega is 2 pi f. So times 100 pi. Pi will cancel pi. So kindly put it in the calculator. 100 pi. And you get the answer to be 55.37. 55, yeah, 55.4. So this is the answer. So we're supposed to find the DC current, right? That's the ID. That's the ID flowing through the circuit. So let's see if we find another a single phase question. So we are solving the single phase, diode. Okay, so that's it for those questions. Come again. So this is a solution. So we are using the VDC formula here, but we know VDC. We are supposed to find ID rather. So make ID the subject. So pi, we know VDC 205. LS is inductance, supply inductance 1 milli. Omega is 2 pi f, 200 pi. All right, let's move on. Now let's move on to this question here. A step down chopper. Now a DC step down chopper is the same as a forward converter. It's the same as a forward converter or a step down converter. All right, so that's the first thing you must note. So let's try to sketch. Let's try to draw what it is. So we know that a step down converter, it has an inductive load of 1 ohm resistance and 10 millihenry inductance. All right, so 1 ohm resistance, 10 millihenry inductance here. Source voltage is 24 volts. Source voltage is 24 volts. On time is 8 milliseconds. So frequency is what? 100 hertz, right? They said the on time. Watch. This my drive, right? We say wait, this is our what? This is our DT. This is our 1 minus DT, right? So this is the on time. So yeah, they've given me the DT straight for like the time itself. So DT is given by 8 milliseconds. So they didn't give us the DT, they give us like the actual on time. That's the DT at 8 milliseconds. All right, find the maximum load current. Find the maximum load current. So we're supposed to find. So the load current is what this. You know that is IL mean, right? That goes through IL mean. So we're supposed to find the peak value of the IL mean. So let's find the current. Let's find the load current. Let's find. So we are just supposed to find the load current. Actually, the load current. So we know that V out over VI for forward converter is equal to D. Right? It's equal to D. For me, I can find my D as well. D is equal to 8 milliseconds over period. So they said that the output is made up of what? A resistor and an inductor, right? But in the steady state, the voltage across the inductor is equal to what? 0. So this V out is seen across the resistor here. So I can use that to find my Current load output current is given by what? V over R. I is V over R, right? So my V is 19.2, R is 1. So the answer is 19.2 ohms. The answer is 19.2 ohms. Yeah. So please watch the solution. So it was a forward converter, as we can see here. Right? So we're giving input supply, we're giving supply. Yes. Sure. All right, please let's move on. So yeah, so this is it. So we're giving the on time, that's our dt. So we can find d from here, then use this formula to find our v out. Once I have v out, I can continue. All right, so let's see we have a question on the dc. So watch, we say dc step down chopper, dc step down chopper, dc step down chopper. Is it tomorrow? Because it to be like tomorrow's going to be arranged in order. Like if it's one topic, it will be one topic. This one because it was online, that's why it's like that. So look for a DC step down chopper. I can't see. Okay, so I guess that's the only question that came. Okay. Okay, the same question, same question. 19.2. Alright, sure, let's move on. A boost DC to DC converter. Boost, a boost DC to DC converter. Yeah, that's what I just said right now. Was boost, easy boost. Alright, so this question is a boost DC to DC converter, so you have to take it easy, alright? Hope you guys get it. Sure. So let's see how a boost DC looks like. So a boost DC is like this. That one, we have what? We have the inductor here, we have the switch here, we have the diode here. Alright. So it delivers an average current of 3 amps. So an average current of 3 amps into a 10 ohm resistance. So I can find my V out as what? V out is what? 30 volts. Yes. Oh, you guys are not helping me. V out is 30 volts. I'll make sure. The source voltage is 12 volts. So we have source voltage 24. 24. 12. I'm reading the question. Inductance is 20 microhenry. 20 microhenry. C is 100 microfarad. 100 microfarad. Frequency is 50 kilohertz. F is 50 kilohertz. Find the output ripple voltage. Find the output ripple voltage in volts. The output, we know that what? Delta V is equal to what? Current time area over C. Right? Because the current time area over C. Now, for the boost, the current time area is it's simple. Okay. I'm coming. I'm checking. I'm checking if it's work. I'm coming. Oh, I'm coming. Why am I getting a little confused here? I'm coming, please. The thing is plenty here. Things are a lot. So yeah, I get delta V to be equal to what? VD over RCF. Because this become F, it will come down, sure. So V out, V out over VI is what? So here boost to is 1 over 1 minus D. So 1 minus D is equal to V in 12 over V out 30. D is equal to 1 minus 12 over 30, right? That's what 18 over 30. That was 6 over 10, so 0.6. So D is 0.6. D is 0.6. So I think we have everything we need. But this V, what is it? No, let's see this way. I'm coming. R is what? R is 10 times C. C is 100 microfarad times F. Charger. Alright, 0.36. Hey, go stay by the bell. See, I should refer him, man. Just really like something like tomorrow if I can solve myself, but I don't want to check because I'll become very familiar. Yeah, so that's it. I'm good. So we are using, so like, let's go back. We are using the fact that del V is equal to current time area over C, right? And then I'm saying that the current time area, current is what? Current is V over this one. Yes, this one is more formula. With current is V over R, right? Current is V over R, but it is like VI, V out. Sorry, how can I mean VI over R? So V out over R is the current, right? That's the current. Then times the time. The time is what? DT. The on time is DT. So times DT over C. Then I found my D. I know that for forward, for boost, V out over VI is equal to 1 over 1 minus D. So I use this to find my D here, which I did. You get D to be 0.6. T is also 1 over F, so I can cancel this and bring times F down here. I can also bring my R down here. So after I did V out, 30 times D 0.6 over R. R is 10 times C, 100 microfarad times F, 50 kilohertz. That'll give you 0.36. Alright, so this is the answer. Sure. Check if you see a boost DC. Check if you see a boost DC. Or it's the same A. So it's a different current. It's a different question. Sorry. So the same preamble, but here they say find the source ripple current. Find the source ripple current. Yeah, can't go there. Just save me. Can't back. I hope I'm not muted. So we know that delta I given by what? Voltage time area over L. Right? Now let's analyze the circuit here. In the on state, when I close this, what will happen? When I close this, what will happen? When I close this, the current will flow here. Right? To flow here. Because this will now become a short circuit, so the current will flow here. Now when I open this, it supplies here. Right? So when this is closed like this, so for the DT, when this is closed, the voltage across this the voltage across the inductor is what? There's nothing going through here, so it's 12. Because nothing is going through. So the voltage across this one is called to VI. And then when this is now opened here, the voltage here becomes what? V out minus VI here. So if I want to find the area, I can just use this first part here. We've been doing this thing since. So it's this times my voltage time area is VI dt. So the R will be given by VI, that's 12 times dt. We found d to be 0.6. T is the same as frequency, so 50 kilohertz. Then L was given as 20 microhenry. So kindly do this. Remember that you know the question there. The question must still think. I don't like that. So you get what? You get 7.2. So you get 7.2 ohms. That's the answer. That's the answer. Alright. So we just do this, then use this part. When you close this here, so we are using in the on state. This part will be working. This part goes off. So the voltage here is 0. So the voltage across this is just 12 minus 0. That's 12. That's equal to VI. VI. Then dt. So that's what I'm using here. Alright, so is there any other boost? A boost DC converter. Okay, so this question is to find the duty cycle. So I'm sure if it was in order, first duty cycle, that's what we found to be 0.8, 0.6. Then the follow-up questions to follow. Okay, so it's here. So duty cycle is 0.6 here. Okay, all right. So a boost DC. All right, so that's it for the boost DC questions. Sure. So we've not done this. These are AC regulators. We've not done it. So we've not done this. AC regulator. We've not done it. All right. So this is a three-phase fully controlled bridge rectifier. Is fed from this. So this is what is diode bridge rectifier is three-phase. So this diode bridge rectifiers. Diode bridge rectifiers. Right, we know the formulas for diode bridge rectifiers. So the first question says that find the RMS line current. So we know that, and I said that for single phase, the total RMS current is given by what? Single phase given by ID. For three phase, I total RMS is ID square root of beautiful. So we're giving ID in the question that the diode current is 120 ohms. So you just put it there as 120 times square root of 2/3, and that will give us 97.97. 97.98. So this is the answer. So let's do for a three-phase fully controlled. A three-phase fully controlled. So the same question here is what is the displacement factor? What is the displacement factor? So you know what? DF given by our cos alpha, right? So we've been given the output voltage. So let's see. We know that VDC is given by what? Three phase, right? So that's 3√2 line voltage over pi cos alpha minus 3ID ls omega over pi. So this is the cos alpha I'm supposed to find. We've been given this. We've been given everything. So make cos alpha the subject. You get cos alpha to be equal to, first move this one here. So I'll get VDC mean plus 3ID ls omega over pi. Then I'll multiply by pi over 3√2 line voltage. So VDC, our VDC was this is it provides a small load current at this. This is the output 380. 380. Oh, I'm not with it. So 380 plus 3ID. The ID was what? ID was 120. LS. Inductance was given as fantastic. See this? LS omega is XL. XL is equal to LS omega, omega LS. Reactive impedance is equal to omega L. So it means that they give us the reactance. So that's accounting for these two. So the reactance was 0.122, which we were given as 0.122 here. So over pi. So you multiply this answer by pi over 3 root 2 times line voltage. Line voltage is 415. Yeah, 415. So do it. So pi over 3 root 2 times 415 multiplying. So you get 0.703. 0.703. Okay, a 3-phase fully controlled bridge. That's this one. This one came from here. Let me clean. This solution is for the top. Yeah. So now here they said determine the rectifier delay angle. So we also know that so here I find my cos alpha to be what? 0.703. So I can find my alpha. This implies alpha is equal to cos inverse of 0.703. I'll give my alpha. So if you have my alpha, now I can use the fact that 2IDLS is equal to what? Root 3E over omega multiplying cos alpha plus mu. So I'm supposed to find this mu. That's the is it fine what? So the rectifier delay angle is the cos inverse of alpha. This is the delay angle, sure. So just find the cos inverse of 0.703. That'll give 45.3. So that's it. So what I was doing, I was going to find the overlap angle. So delay angle is given by 45.3. So it means there should be a next question where you find the input power factor. That's what psi df, right? We know psi for 3-phase to be 0.9549, and we got the df to be 0.703. So if you multiply, you get the answer to be 0.671. Find the overlap angle, sure. That's what I wanted to do. So here, overlap angle, we know cos alpha, yes, we know alpha, we know everything. So let's see. So let me find. So 2ID 120 LS omega will give me 0.122 over, this will give me what? This will give me root 2 times 415. You see, we are talking about root 3, and E is what? E is equal to omega LS is 0.1. I'm cross multiplying. So E is what? E is V root 2. That's the line, right? And 3-phase, so divide by root 3. So I'm left with root 2V. Yes, they give us the formula here. So here the formula is root 2 times V supply. So that's what I'm just using. So just know that. So if you wanted the formulas, memorize them in terms of RMS values, because that's how you use them. So here it's become root 2 VL. That's what I've done here. It's equal to cos alpha plus this. But the cos alpha across and become minus. So minus the cos alpha was 0.703 is equal to cos alpha is 45 point something plus mu. So I'll solve this side, find cost inverse. So kindly do it. Let's just do it and get the answer. Let me see. Oh, Greek speed, huh? We get what? Minus 0.653. So find cost inverse of this. Come again. Yeah, cost inverse of that answer. So you get 130. When you find cost, you get 130 is equal to 45.3 plus mu. So mu is 130 minus 45.3. That will give us, where is it? No, let me see something. No, this cos alpha, right? Cos alpha. This cos alpha. Papa, you're not gonna help me. So I'm having this right over root 2 times 415 minus 0.703. This is what you got. Sorry, this place is minus. Hey, this is supposed to be minus. It's supposed to be minus. So what does it change? 9. Okay, so you get 49. Sure, sure. That's where it came from. 3.9. All right, all right. So if here is minus, if here is minus, it means that I must rather move this one here. So here will become plus minus like this. So when you find this one and you do, you get the answer. So just take your time and get it. Okay. We want to solve also. All right. Sure. So a three phase, is there any three phase again? That's it. Small small, we are finishing it. We are finishing it. Let's finish hard. All right. Which of the following power devices is likely to be used in a boost converter? That's a MOSFET, high frequency MOSFET. High power use a thyristor. We wish to charge a 120 volt battery from a 600 volt supply. So you can see that this is a step down. That's a forward because if we are charging 120 from 600, so that's a step down. Step down, switch is here, diode is here, inductor is here. Then you have it like this. We wish to charge 120 volts from 600. So I know that I'll need my duty cycle. So for forward is this. So I get D to be V out 120 over 600. That's what 1 over 5. That's 0.2. So how might this to be my D? Sure. Then it said the average current is 15 amps. So the average current is 15 amps. Right, that's a we know that in that current, the average battery current is that. You know that current is what? It's an inductor current. It's an inductor current. So inductor current A plus B over 2 is equal to 15, right? That's A plus B is equal to 30. Question 1. Now also with with peak to peak ripple of 1.5, that means what? That's the change in the current. So B minus A is equal to 1.5. Question 2. So just let's punch and see what B and A are. 130 1 minus 1, 1.5. So B is 15.75, 14.25. Alright. So find the inductor that must be connected in series with the battery. So find this here. Mean our L is equal to what? L is equal to voltage time area over delta I, right? I can find my voltage time area. For inductor, during the on state, the voltage here is VI minus V out. During the on state, the voltage across the inductor, this is VI, this is V out, so minus V out, right? So I'll just use this part, this first area here. So my L is V out minus VI. VI minus V out, that's 600 minus 120. That's the V times dt. D was gotten to be 0.2. We're given frequency. Okay, we're giving the on time, the chopper on time. So that's the dt. So we've been given the dt straightforward. Okay, so there was no need even solving for the d set. We've been given the dt straightforward. That's the on time as 5 microseconds. So 5 microseconds over delta I. Delta I was 1.5. Yes. Wait, you got 3. Get 16, right? Yeah, you get 1.6 millihenry. You get 1.6 millihenry. So kindly do that. When you do this one, you get 1.6 times 10 to the negative 3 Henry. 1.6 millihenry. So let's see if we wish to charge a battery. Please watch inside. We wish to charge a battery. Do you wish to charge a battery? Papa, please check if someone is asking the question. Okay. We didn't come back to so we made some questions. Alright, let's solve this question. A forward converter. So we have a forward converter. That's what we have here. Yeah, if they don't mention it's not isolated. A forward converter is used to obtain 5 volts at 10 amps. So this is to obtain what? 5 volts at 10 amps from a 12 volt supply. From a 12 volt supply. The switching frequency is 40 kilohertz. The circuit must operate a continuous inductor current down to 4 amps. Right? So we know that we can reduce it till we get to some threshold. So they're giving us a threshold current. At threshold, they say the current, let me call it I01 is equal to 4 amps. Isolation between inputs is not required, so no isolation. Using the threshold condition, determine the inductor current ripple value. So at the threshold, we know that this value represents the delta IL, right? Yes, this value here. And we know that what? We know that the mean area is what? Mean area. The mean value of the current is what? Is the area over the period. So area of this is half times base, that's the entire period, times height, that's delta IL, all over period. And this is what gave us the mean current at the threshold. So therefore, my delta IL is given by 8 amps. Cross multiply, get 8 amps. So 8 amps. A forward converter. A forward converter. Okay. Oh, that's all. That's the only question on that. You could have asked a number of questions if you wanted to, so just read around that side. Alright. In modern times, the most important application of a three-phase thyristor converter operating in the inverter mode is the HVDC power transmission. Is the HVDC power transmission, sure. No, it's in the slides. Which of the following is true? So this question came in the midterm. Or maybe not. That power converters match supply to load, bidirectional or unidirectional, and efficient. So it's all three. Alright. This a triac, we didn't triac, no. Which of the following is not a common application of, don't forget that AC voltage regulator, it will not come. But here the answer is synchronous motors. Okay. Sure. So these questions are like the unit 5 we did right now. So determine the fundamental RMS output voltage. We're given modulation. You know that MI is equal to what? The fundamental peak over E. Right, let's say RMS. So V1 RMS is modulation index times E over root 2. So kindly do this one. You get this answer 169.71. Kindly verify for me, Ajwa. 169.7, that's correct. This will not come. Okay. Why didn't I see this question when I was solving the battery question? Okay, so here, okay, we got B to B, B to B 15.6. So this question, this battery question, we got B to be 15.75, A to be 14.25. They said find the diode current. You know that what? Diode current is what? That's what? A plus B over 2 times 1 minus D, right? We got D to be 0.2. So kindly do it 15.75 plus 14.25, that's 30, 15 over 2 times 1 minus 0.2, so times 0.8. So do 30 times 0.8, what do you get? 12. Okay, so the answer is 12 here. So this one corresponds to the we've Papa, what are they saying in the room? Kindly hold. Papa. Mm. All right. So this question is what? A non-isolated flyback question. Find the minimum inductor current under rated load conditions. So you've been given the rated current as this. The threshold current is this, right? So we should be able to do this one too. All right. Fluid is not an application of power electronics. Induction motor operating direct online, because Toyota Camry, yes, it does like electric system, power supplies, yes, washing machines, yeah, the white goods. So except the induction motors. Wow. All too soon we've come to the end. Oh, I might say I'm rather surprised. It came so quickly. All right. Yes, that's it. So that's it. So that's it for the questions. So be kindly like these questions, but when some will come. Just take your time and go through. Then also the questions that Andrew dropped this evening, the assignment. I think those ones they are just the slide questions, but just like captured in an exam form. So just try and go through all those ones too. All right. Yeah. So we have come to the end. There were a lot of ups and downs on this stream. A lot of things have been coming up, but then at least you try to cover everything. We've solved the examples. So kindly go through and feel very confident. All right. Yeah. So okay, I left this question. So let's look at this question. Very hard. Very fair. So please, if you don't watch your old video, kindly watch your old video because I refer to this question in the old video. All right. So let's just deal with it. All right, sure. So this seem so we know that in these questions we said that we have some VI, V1 supplying to V2, right? And then the VL is here at some delta. Fine. Now they say that what if the output power is maintained at the same, so we maintain the output power. So our PDC is maintained. We have 4,800, which means our PAC is also the same. Our PAC is also the same, 4,800. Now they say we have reduced the modulation index is changed to 0.65. So now we have a new MI, right? This how don't forget this is how the circuit looks like. Oh. So I have the AC here, V1, I have my V2 RMS here, I have my E here. So the MI is changed. So at the new MI, there will be a new V2. They say E is kept constant. So then I'll just say that. So I'll just say, oh, modulation index MI is equal to V2, that's a fundamental, right? Peak over E. So the V2 fundamental peak is given by what? Mi is changed to 0.65 times E. Is it 500? 0.65 times 500. So let's do that. 0.65 times 500. Please, what will it give us? It give us 325. So let's find the RMS. 325 over root 2. 229.8. All right. So this means that at this new modulation index, this is the new V being produced. So which means that I'm saying that okay, I have my V1 240, right? V There will be some V2 produced that's less than the V2 initially. So there will be some my lines are not straight, sorry. So there will be some V2 produced too. This V2 is 229.8 at some delta. Now at this new V2, there will be, you see, initially we said that there's unity displacement factor, meaning that the current was in phase with this voltage, but now when we change the modulation index, the current won't be in phase, so the current will be here, right? So the idea is that we want to find this displacement factor alpha. So this is how you go about it. We want to find the displacement factor alpha. Now see, this place is my VL. So here's how you go about it. This is how you go about it. First, find your delta. When you find your delta, use your delta to find VL. When you find VL, the angle for VL is this angle here, because it is this VL, right? So the angle for VL will be here, let's say beta, and that angle will be the same angle here, beta. So if here is 90, meaning alpha is 90 minus beta. Means alpha will be 90 minus beta. So let's find delta. We know that the power produced between AC sources is given by what? V1, V2 over X and delta. So delta is P, right? That we say the power remains constant times X. X is 2 pi FL. So let's see if we have X is 2 pi FL. Yeah, so we have everything. So as 100 pi times 5 milli. So 100 pi times 5 milli over V1. V1 is 240. V2 is 229.8. So find sine inverse of this. I get in 7.85. 7.85. So so delta is 7.85. But don't forget that this is lagging. Don't forget that it's lagging. You can see, which means that my V2 is given by 229.8 angle negative 7.85. That's V2 here, right? Sure. So therefore, in vector wise, my VL is given by this minus this. So VL is given by 240 angle 0 minus 229.8 angle negative 7.85. So when you do this correctly, you get something. 240 angle 0. 240 angle 0 minus this. So when you do this, you get this. You get 33.7. You get 33.7 angle this. But all I care about is the angle here. I said I want to find, so when I found the angle here, because the angle for VL is this angle here. This is the angle I found. So then my alpha is 90 minus that angle. And then I'm supposed to find displacement factor. So I'll find cos alpha when that you get, yes, so we are finding cos 90 minus this angle here. That give us this angle. We found this angle which is equal to this angle here. Z angles are equal what here. So I'll find here. So you get 0.931 as the final answer. And that brings us to the end of our electronic stream. Hopefully, please, if you have any questions, just send it to the group. We'll be around to solve them. Thank you very much for your time. All the best to you tomorrow. Take care of yourselves too.